Good morning, everyone. I would like to thank Professor Takesti for inviting me to give a talk at this ISTVS ISU symposium. The topic of my talk is the Bevameter technique, its present and future. The contents of this presentation include an introduction to the cone penetrometer technique and the Bevameter technique, the basis of the Bevameter technique, the current practice of the Bevameter technique, the need for an updated recommended practice for the Bevameter technique, and closing remarks. To study or predict the performance of off-road vehicles, including farm tractors, and understanding of the engineering properties of the terrain or soil on which vehicles operate is essential. Currently, there are two major techniques widely used to physically measure the engineering properties of terrain for the study of vehicle mobility. One is the cone penetrometer technique, and the other is the Bevameter technique. The cone penetrometer technique was pioneered by Waterways Experiment Station of the United States Army Corps of Engineers for evaluating military vehicle mobility on a go or no-go basis and for assessing terrain trafficability. This technique is also used in agriculture engineering for identifying soil conditions for farm machinery operations, in geotechnical engineering for evaluation of site homogeneity and depth to firm layers, voids, or cavities, and other discontinuities. Corresponding standards have been established by ASAE, ASABE, ISO, and ASTM. The resistance to cone penetration reflects the combined compressive and shearing characteristics of the terrain and adhesion and friction on the cone terrain interface. The contribution of each of these factors to the cone resistance cannot readily be differentiated. As a result, the cone penetration resistance per unit cone base area, the cone index in PSI, or the cone index used in the defense sector without units attached, is primarily used for developing empirical relations for predicting off-road vehicle performance. For example, the empirical soil tire numeric NCS is equal to C, the cone index, B, the tire width, D, the tire diameter, over W, the normal load on the tire, is used to empirically predict tire performance, such as the drawbar pull coefficient and drawbar efficiency at 20% slip on cohesive frictional soil. For example, if the value of NCS is 40, then we can make use of this curve and estimate the drawbar pull coefficient at 20% slip is approximately 0.6. Making use of another curve, we can estimate that the drawbar efficiency at 20% slip is approximately 0.7. The two curves shown in the previous figure were based on test data with tires ranging in width from 14 to 33 inches, in diameter from 33 to 65 inches, and in load from 495 to 6,500 pounds on soils ranging from tilled to untilled. It should be noted that these empirical relations are valid only for tires of similar design and dimensions under similar soil conditions. It is by no means certain that empirical relations can be extrapolated beyond the conditions upon which they were derived. Furthermore, a number of factors that are known to have significant influence on tire performance, such as tire inflation pressure, tire construction, bias or radial, and tread pattern, have not been considered in the empirical relations between NCS and tire performance parameters. In view of the limitations of empirical methods, physics-based methods using appropriate terrain parameters for predicting off-road vehicle performance have been developed. The basis of the Bevameter technique. An off-road vehicle, such as a truck vehicle shown in this diagram, through its running gear, applies normal load to the terrain surface, resulting in sinkage and associated motion resistance. The torque applied to sprockets of a truck vehicle or tires of a wheel vehicle initiates shearing action on the vehicle terrain interface and results in the development of thrust. To measure terrain properties pertinent to vehicle mobility, a device was developed by Dr. Bekker to measure the pressure sinkage and shearing characteristics of the terrain, which has become known as the Bevameter or the Bekker value meter. This photo shows a vehicle mount Bevameter. This part of the Bevameter with a shear head is to measure the shearing characteristics of the terrain. This part with a shaft attached with a sinkage plate is to measure the pressure sinkage relationship of the terrain. The Bevameter technique has since been further developed to include the following three measurements. First, terrain response to repetitive, normal, and shear loadings for predicting the effects of passage of consecutive tires or road wheels on the performance of multi-axle wheel vehicles or truck vehicles. For example, if we consider an element of the terrain on the surface under a two-axle wheel vehicle, then this element of the terrain is first subject to the loading of the front tire, and the pressure sinkage relationship will follow this loading line. If at point A, the pressure applied by the front tire decreases, then the pressure sinkage relationship will follow this unloading line. If this unloading line is inclined and not vertical, then it will imply that the terrain may have a degree of elastic rebound. This distance represents the rut depth created by the front tire. As the vehicle is moving forward, this element of the terrain will be subject to the loading of the rear tire. In this case, the pressure will start from zero and then will follow the reloading line. If the normal pressure applied by the rear tire is higher than that by the front tire, then the pressure sinkage relationship will follow this line. If at point C, the pressure applied by the rear tire decreases, then the pressure sinkage relationship will follow this unloading line. This distance represents the total rod depth created by the front and the rear tire. The second measurement is the rubber terrain sharing characteristics. This is for predicting the traction of rubber tires or rubber tracks. The third measurement is the vehicle belly material terrain sharing characteristics. This is for predicting vehicle belly drag if the belly sinkage is greater than ground clearance. This will occur if the vehicle operates on a very soft terrain, such as deep, fresh snow on a frozen ground. Parameters describing all these characteristics are now referred to as the Bekker-Wong parameters and have been adopted into the 2020 ISTVS standards. The current practice of the Bevameter technique for pressure sinkage tests. In the early days of development of the Bevameter technique, rectangular plates with high aspect ratios of length to width were used, as the rectangular plate was considered to be similar to the contact area of a track. Later measurements have shown that under the track, load is more concentrated on track lengths under road wheels, as shown in this diagram. Also, the contact area of a tire is close to an ellipse, as shown in this diagram. Consequently, circular plates with areas of the same order of magnitude as that of the tire or track length are now widely used. If the Bekker equation is used to characterize the pressure sinkage relationship, that is, P, the pressure, is equal to Kc, a terrain parameter, over B, the radius of a circular contact area, plus K phi, another terrain parameter, multiplied by Z, the sinkage, raised to the power of n. Then 3 terrain parameters, Kc, K phi, and n, have to be determined. Test data should then be obtained using at least 2 sizes of plates. Plates of diameters of 7.5 and 10 centimeters have been used. In SAE J939, a recommended practice for off-road vehicle mobility evaluation, published in 1967, the values of Kc, K phi, and n are recommended to be derived graphically by plotting the test data obtained using 2 different sizes of plate on log-log scale, as shown in this diagram. N is determined by the slope of the lines, represented by the tangent of this angle beta. Kc and K phi are determined by these 2 relations respectively. A1 and A2 are the pressures at sinkage Z equals to 1 of the two plates. B1 and B2 are the radii of the two plates. This graphical method relies on the subjective judgment of the investigator in plotting test data on the log-log scale and is liable to errors. Also, the values of Kc and K5 are determined only by the pressures on the two plates at Z equals to 1. A method for processing the pressure sinkage test data based on the weighted least squares principles has been developed to replace the graphical method mentioned earlier. Taking logarithms of both sides of the Bekker equation, one obtains this expression. Applying the ordinary least squares principles to the logarithms or deviations will give excessive weight to the deviations at low pressures, which are usually the least significant. However, one may approach the issue by introducing a weighing factor p squared, or the pressure square, to obtain the optimal values of Kc, K5, and N by minimizing the following function. In this function, p squared is the weighing factor. This proposed weighted least squares method has been well recognized and cited as very reliable. The Bekker pressure sinkage equation discussed earlier is based on an equation for relating the pressure and settlement of structures or foundations in civil engineering soil mechanics. It indicates that for the same sinkage Z, the pressure P required is lower for a larger contact area represented by B. Test data obtained in the field under natural conditions sometimes indicate that at the same sinkage Z, the pressure P measured is higher for a larger contact area. This leads to the value of Kc being negative, or the measured pressure sinkage relationship does not follow the trend indicated by the Bekker equation. Under these circumstances, equation P equal to Kzn, K is the terrain parameter, may be considered as an alternative in the case that the pressure sinkage equation is independent of the size of the contact area. The current practice of the Bevameter technique for shear tests. In the early days of development of the Bevameter technique, the rectangular shear plate with a high aspect ratio or length to width was used, as it was considered similar to the contact area of a trap, as shown here. To maintain the rectangular shear plate in a horizontal position during tests, a double parallelogram must be employed, as shown here and here. The front grosser of the shear plate, shown here, generates a bulldozing force which will complicate the processing of the test data for determining the shear strength of terrain. Because of this and other issues, annular shear plates are now widely used, particularly in field tests. Annular shear plates with outer and inner diameter of 34 and 27 centimeters with a ratio of 1.26 have been used for field tests. To obtain the terrain internal, rubber terrain, and vehicle belly material terrain sharing parameters, shear plates with grousers, rubber, and vehicle belly material are used, as shown in this photo. To maintain a constant normal pressure on the shear plate during tests, dead weights or hydraulic accumulators, when normal pressure is applied hydraulically, are used. Soil conditions may generally be classified as loose or dense. In the loose state, the shear stress-shear displacement relation may be represented by curve A. In this case, the shear stress increases exponentially and approaches a maximum value. In the dense state, it is represented by curve B. In this case, the shear stress initially increases rapidly. It reaches a peak value, and afterwards it decreases and approaches a residual value. In the loose state, the shear stress-shear displacement relation is usually expressed by the following simple exponential equation, as indicated here. In this equation, S is the shear stress at shear displacement J. S maximum is the maximum shear stress, and K is the shear deformation parameter. A weighted least squares method has been used to derive the appropriate value of K in the equation for characterizing the shearing behavior of soils in the loose state. The value of K in the range of 3.0 to 4.1 centimeters on a sand was obtained using an annular shear device with outer and inner diameter of 34 centimeters and 27 centimeters respectively. On the same sand, tests were performed using a full-scale vehicle where these tracks lock up by applying brakes to the sprockets, which is equivalent to using the track system as a linear shear device. From the measurements of the horizontal pulling force applied to the vehicle and the horizontal displacement of the track, the value of K was about 3.6 centimeters, which was within the range of 3.0 to 4.1 centimeters obtained using an annular shear device. The test results are shown in this figure. The vertical axis is the horizontal pulling force applied to the vehicle. The horizontal axis is the horizontal displacement of the track. The two solid lines represent the measured data. The dashed line represents the fitted curve based on the test data. Using the weighted least squares method, from here we can see the value of K is 3.6 centimeters for the fitted curve. This indicates that the value of K obtained using an annular shear device can be used to characterize the shearing behavior of a full-scale vehicle. In the dense state, the shear stress-shear displacement relationship shown by curve B may be expressed by this equation. In this equation, Kr is the ratio of the residual shear stress to the peak shear stress. Kw is the shear displacement at which the peak shear stress occurs. The value of Kw can easily be identified from the measurements, and the optimal value of Kr can be obtained by the ordinary least squares method. The equation for the shear stress-shear displacement relation for terrain in the dense state has been widely used for describing the shearing characteristics of various types of terrain, including compact soil, sintered snow, and seabed terrain at thousands of meters below sea level. For example, in the development of a deep seabed polymetallic nodules harvesting system with trapped undercarriage, this equation has been used. Applications of the Bevameter technique. The parameters derived from the Bevameter technique can be physically related to off-road vehicle performance parameters, such as vehicle sinkage, motion resistance, thrust, and drawbar pull. The Bekker-Wong parameters have been widely used in the development of physics-based models, such as our NWVPM for wheeled vehicles and NTVPM for truck vehicles, for predicting the performance of terrestrial off-road vehicles and the mobility of extraterrestrial rovers. As an example, in collaboration with NASA Glenn Research Center, we conducted a study to evaluate the capability of the simulation model NWVPM using two lunar roving vehicle wheel candidates as an example. One is the wire mesh wheel, and the other is the Hope spring wheel. The predicted performance using the Bekker-Wong parameters was substantiated by test data. The Bekker-Wong parameters are also used as terrain input to the simulation model NTVPM for predicting truck vehicle performance. An example for predicting the performances of a military vehicle on sandy terrain, muskeg, and snow-covered terrain is shown in these figures. For example, on the sandy terrain, the measured drawbar pulls at different slips are represented by the data points. The solid line represents the predicted performance using NTVPM with the mean values of the Bekker-Wong parameters. The two dashed lines represent the performances predicted with the upper bound and lower bound values of the Bekker-Wong parameters. The predicted performances correlate reasonably well with field test data as shown in these three figures. The Bekker-Wong parameters of these three types of terrain and the correlations between the predicted performances obtained using NTVPM and field test data are adopted as benchmark data for the next generation NATO reference mobility model in the NATO standard AMSP-06 Annex F published in 20 21. The need for an updated recommended practice for the Bevameter technique. While the role of the Bevameter technique in the evaluation of off-road vehicle mobility has been well recognized, there are no standards for this technique established by professional organizations. On the other hand, standards of the cone penetrometer technique have been established by various professional organizations such as ASAE, ASABE, ISO, and ASTM. For the Bevameter technique, it appears that so far there is only one recommended practice presented in SAE J939 Off-Road Vehicle Mobility Evaluation of 1967, almost 60 years ago. There is a need for an updated recommended practice for the Bevameter technique established by professional organizations like ISTVS or SAE. The development of an updated recommended practice for the Bevameter technique. With the experience accumulated in the past few decades, the time is ripe to develop an updated recommended practice for the Bevameter technique with the following purposes. First, to provide specifications for the Bevameter technique that facilitates the reporting and interpretation of terrain data by different users. Second, to provide a common approach to characterizing terrain engineering properties measured by the Bevameter for developing physics-based prediction models for off-road vehicle mobility. The updated recommended practice is to specify the following. For pressure sinkage tests, the size of circular plates, the penetration speed of the plates, the range of normal pressure and sinkage for the plates, the procedure for measuring terrain response to repetitive normal loading, and the method for characterizing and processing pressure sinkage test data. For shear tests, the outer and inner diameters of the annular shear plate, the surface features of shear plates, such as growler arrangements, rubber material, and vehicle belly material, the rotational speed and the maximum angular displacement of the shear plate, the range of normal pressure applied to the shear plate, the procedures for measuring terrain response to repetitive shear loading, the measurement and characterization of sinkage shear displacement relation for predicting slip sinkage of off-road vehicles, and the method for characterizing and processing shear test data. Closing remarks. The roles of the Bevameter technique in characterizing terrain engineering properties and in developing physics-based models for predicting off-road vehicle mobility have been substantiated and recognized. To provide a common system for measuring and characterizing terrain engineering properties, the time is ripe for professional organizations like ISTVS to establish an updated recommended practice for the Bevameter technique. The references noted in this presentation are listed on this page and on this page. Thank you for your attention.